And again, hopefully I am live. Let's just see. Yep. Here we go again with another guy that simply doesn't understand. The topography of the land can change underneath the water, and it can change what you're seeing over the water. How you showing, Walter? Nice to see you in. You're the first one in for sure. This is a response video as such. You know, you can say it's a response video, even though I haven't actually been asked specifically by Dazza the Cameraman to look into this. But it is in response to a video that he's released recently. I'm just going to get into that right now. So I'm just going to share my screen. I know this is the second one of the day, guys, and I do apologise, but it's what we have to do. Because it's time to confront these globy zealots and show them that they are mistaken when they are looking at something in the distance and they think that the boat is sinking. Indeed, it isn't actually sinking at all. Now, this all spawns from, let me just hide that, this all responds from Anthony Riley here, who is pretty active on, I'm not even sure what it is that he's active on, but he's active on some kind of forum or something. And Sean G has asked him to look into this this video from Dazza the Cameraman, and Anthony just messaged me and he said, look, can you take a look at this and ask me what you think? It's interesting that in his response, Anthony's already started to look into things like tidal bores and riptides, which is fair enough because that is a very reasonable explanation. But in this particular case, it's more to do with barotropic tides than anything else, and I'm going to show you why. And I'm also going to show you why this location, which has been shown many a time to show this kind of phenomena, which I personally have never ever seen. This phenomena is, renowned for this type of observation, and I'll show you how it can happen, what's causing it, and we'll go into that right now. So, without further ado, we're going to look at his video. So obviously, we're doing this for educational purposes, etc. He's claiming, what is he claiming actually? Let's just see. Here is the raw video I used in my recent video. Does more zoom cause ships to come up over the horizon? So by actually putting that term in there, horizon, what he's actually saying is that there's a curvature of the earth in the way. Well, let's have a look. Let's have a look, shall we? We don't have any GPS for this, so it took me a little while to find the exact location, but I've managed to do that. We have two boats. Apparently one's 8 miles away, one's 12.6 miles away. I'm just going to play the video a bit. Knock that off. So the boat in the near ground looks like it has very little, if any, inferior mirage on this particular day. Just looks like it's a bit hazy more than anything, but we clearly do have a good line of sight to the first boat. The second boat, however, it does appear that the hull is not visible. So we're going to give him that. We're going to say yes, from your camera. In this particular instance, the boat's hull appears to be hidden. Now, why is that? Because in this location, it seems that this is a very frequent thing. It's the first time that he's put observations out just like this. First thing I want you to concentrate on, though, is the movement of the water. So what we're going to be looking at is which way is the water moving? Is it moving from left to right, or is it moving from right to left? So let's play the video. Right, this is the important part. We've gone past the tide swells at the seashore. Now we're looking at the actual movement of the water. So is the water moving from right to left, or is it moving from left to right? So as he's looking at this boat, it's quite obvious that the movement of the tide is from right to left. It's definitely moving from right to left. Now then, let's show you his location. I've managed to find it and triangulate a few interesting points. So here's where he's taken his observation from. He's taken it from a car park right down here next to Omaha Beach Surf Lifesaving Club. I would assume he's in this general location here looking across these bushes. But what you will see is as the tide is moving from right to left, what that means is that the tide is actually coming in. So let's just put a line of sight to that. So from his location there, we've got the tide moving from this direction into this direction, meaning that the tide is actually pushing inwards as opposed to receding outwards, right? So if it had been going from left to right, the tide would be going out. As it so happens, the tide is pushing in, so it's going from right to left. So we have an incoming tide. Let's look at some interesting points about topography of the land, because globers seem to have this idea that the topography of the land doesn't alter things on the water. Well, I'm going to disprove that in a moment. We're looking where this boat actually was, and this is a rough estimate. I'm not entirely sure that this is 100% accurate, but it's within a margin of error. It's probably within a mile or so of this exact location. So we're looking at the elevation above the water. Well, in the bottom here you can see elevations. So we've got -49 where I'm hovering over the cursor here. So when I pop it over there, we've got -21 meters. So it means that the boat is essentially 21 meters above the seabed. The seabed is approximately 65 feet or thereabouts beneath the water. What we need to look at then is, how does the topography of the land change the further out you go? So let's go over here, and we're just moving probably another 8 or 9 miles further away, and we're looking at 89 meters along this entire shelf, 89 meters all the way down to here's again 83 meters. So it's quite a substantial drop. We're talking at this depth here, it's 250 feet. Obviously at this depth it's 60 feet. So from 60 feet it's sloping away, it's getting deeper and deeper and deeper. It goes down to 250 feet. Let's go out another 10 miles or so, and we've got another 10 miles, and we go along this stretch of line here. We've got 600 meters, 600 meters, 600 meters, all the way across here to 600 meters. So essentially it's a 600 meter shelf there, so about 2,000 feet or so. So in the space of probably 20 miles, so the distance that I look from my location at Ankersholm, looking at Barrow in Furness, we're looking about that sort of distance. What we've got here is the topography of the land underneath the seabed changing from a depth of 2,000 feet to approximately 60 feet. I'm going to show you what that looks like on an image, just to give you an idea. So obviously down at the bottom here we've got, let me just get it a bit nearer so you can see, there we go. So we've got 2,000 feet deep here, and we've got all this water sitting at a depth of 2,000 feet, and then it slopes up, it's sloping up, it's sloping up until we get to a point here. We've got a boat sitting on a shelf. I've put it essentially 200 feet deep because I wasn't entirely sure whether it was 200 feet or it could be 60 feet. It's in that location. So we're going to go for anywhere between 200 or 60 feet, somewhere in this general location. It's shallow and this is deep. And we notice that the tide is pushing in from right to left. So the tide is pushing in. So it's coming across this shelf. So it's pushing in against the shelf. Now then, I want to talk about barotropic tides and what they do, and where they actually, where this barotropic tide is actually most pronounced. I've actually included that here. This is the general area where the barotropic tide is going to be at its most pronounced. That will be where you've got all this water pushing in as a tidal force into a bottleneck. Now this is a bottleneck. This area here is a bottleneck. It's very narrow, very shallow, and you have 2,000 feet deep of water, tide force pushing in into a very narrow spot. It's going to cause something called a barotropic tide. Now, what do barotropic tides do? Let's have a look. What is a barotropic tide? Now, this is just somebody's comment, somebody's personal words that they've written this in. There's no reason to take this as kind of a citation, but he explains it quite well. You can research this yourself, and I will go into this in a bit of detail further on. Let me just zoom in so you can see. Okay, so when the water being forced by the barotropic tide encounters undersea topography, just as I've explained, the water is diverted vertically, so up, where it can encounter a different surrounding density. Right, so obviously we're talking about a vertical push here, exactly as I have explained. Let's now look at sciencedirect.com, and we'll look at barotropic tides. This is interesting. Dazza The Cameraman, you know, this is something that you should know, because just asserting that its Earth curvature is just showing how limited you are in your research, because this is pretty easy to understand. In my location, we don't have this this fall off, this shelf. We don't have this shelf. It's very level. It's roughly around about 60 to 80 meters across the whole section in the in where I film. You've got this massive shelf, and you should understand this. When we speak of tides, we usually refer to surface barotropic tides, which have nearly uniform current velocity from top to bottom and a maximum vertical displacement at the surface. However, there is also a class of internal baroclinic tides with velocities that vary with depth and with a maximum displacements in the interior. A surface barotropic tide has essentially no shear in the interior ocean. There is a shear near the bottom boundary, but the barotropic tidal velocities are so low in the deep ocean that the dissipation is negligible. So let me just show you what that means on this particular image here. So basically it's saying that the barotropic tidal force in this area here, which is obviously pronounced at the surface, is negligible. It doesn't have any effect of it in the deep ocean. That's basically what that says. However, it goes on to say, in shallow seas, the barotropic tidal currents are amplified, and the dissipation proportional to the current cubed is greatly amplified. Now that's really important to understand. What it's saying there is that in the deep ocean, it has no effect. The barotropic tide has no effect in this area. So let me just put a little box in here just to give you an idea of what that means. And what we're going to say is that this is in the deep ocean. The surface area, the barotropic tide forces here are negligible. They don't really have any effect in the deep ocean. However, they are amplified when they encounter the shallow water. And barotropic tides only happen when you have this shelf, this massive drop off, and an incoming tide. So all the conditions that Dazza The Cameraman was filming in are absolutely perfect for a barotropic tide to be causing this obstruction of the boat. Lastly, I want to show you I've put barotropic tides vertical gradient. Called barotropic flows, they are driven by horizontal pressure gradients induced by the sea surface slopes accompanying the tides. There we go, the sea surface slopes accompanying the tides. Internal tidal currents vary with depth, unlike barotropic tidal currents, and are associated with vertical displacements of 10 meters or more in the thermocline. So let me just show you again what that actually means. That means that in this location, well, let me bring that box over. That's what it's saying is that 10 meters or more, there can be a localized bulging of 10 meters or more in this location. Now 10 meters, that's essentially, you're looking close to 35 feet there, right? 35 feet of bulge that is caused by the tidal, by the barotropic tide, or more, depending on the strength of the current, obviously. And I want to go on to look at in the thermocline, right? So 10 meters or more in the thermocline. So what is the thermocline? Let's look at the thermocline. Let's have a look at an image of the thermocline. Here is an image of thermal stratification in the thermocline. It's the difference between the cold water and the warm water, and it's also on a shelf. and it happens on a shelf. Just like, funnily enough, look at this image. Look at this image. I'm going to copy that image. And when we look at the image that I produced earlier on, and we overlay it here, let's get rid of that. And look at that. There we go. Thermal stratification. We have the cold water, we have warm water. The barotropic tides happen in this exact location where we've got cold, deep water being pushed into the warmer, relatively warmer waters at the surface, and also on a slope just like this, just where Dazza the cameraman is doing all his observations. So in these locations here, where these boats are traveling over this slope, or the top of the slope here, that's where all this 35 or 40 feet or even more of localized bulging is happening. This is where it's happening, and Dazza the cameraman is filming this. So he's actually not filming across a level surface, he's filming across an area that is renowned for barotropic tides. I can go further and I can show you just how deep this actually goes. If we go further out to sea here, you can see, get an idea of how deep this area is. We've got 1,366 meters in depth along this shelf here. So essentially we're looking at around about 5,000 feet. We've got 5,000 feet deep there. We've got 2,000 feet deep here. We've got 200 feet deep here. And then we have the boat itself, which is situated roughly around about 60 or 80 feet deep. So exactly in the location where these barotropic tides are. It's got nothing else to go against, it's just offshore. So you've got all that water pushing in, all the water pushing in from here, all that water pushing in to the shoreline, and the boat is being affected by a barotropic tide. That's what's causing the hull of the boat to disappear. Dazza the cameraman, you should look into this. You're in that area yourself. You should know this. It's your own location. I'm surprised you don't look into this stuff. It's something that I've been talking about for a long time, and it's something that we're all starting to understand now. This is localized bulging. This isn't earth curvature, and you should know better. Everything in that video gave it away. If we look at the video and just one last time, we'll look at the video, you can see that the tide is actually pushing in from right to left, proving that the tide is being pushed in across that shelf, bringing the colder water to the surface, causing the barotropic tide, or a 10-meter or more bulge, localized bulge, between ourselves and that boat. That is what is hiding the boat, Dazza the cameraman. So I'm just going to give a few shout outs to people that are watching. Let's see, let's start. Jason of the Didsbury family. Hi Shane. Perfectly explained, which explains a lot of the footage we've been presented. Yep, it does. They're miserable people, dabbing good, walking around citating people dead. Well, no idea what that's about. Rambo Jambo, Rhett Priestley, nice to see you in. Ryan Hugh Vincent, Darla, nice to see you in. The Ham, cool stuff. Daz Studio. Ali B, nice to see you in, mate. It's interesting to understand this, because I'll just go further and show you my location, because on my side of the world, where I do my filming. So here we go. And this is what I'm gonna. This is how I'm gonna explain it. How we never get to see this here. I never get to see a boat disappear over the curve, you know, or have 3/4 of the boat hidden, or half of the boat hidden, as some of these other people do. And again, we're going to concentrate on this this elevation down here. So we've got -meters. So let's go back to where I do my filming from, which is essentially here. So let's look across to Barrow and Furnace from this spot here. And what we're going to do is we're going to look at the depth. So we've got 14 meters, 9 meters, 0 meters, 1 meter, 8 meters, 10 meters, 16, 20, 16, 18. It's nothing. There's no real depth changes there. It's very level, very flat, and the water stays flat. And that's what's very interesting, is that because we're looking across an area of topography of the land that's relatively, in fact, let me draw it. That'd be easier, wouldn't it? So that would be easier. I'll do it on that here. Right, so this is the area that I'm going to be looking across. This is essentially my view of where I'm looking across. Something like that. That's it. So when I'm looking across, the water is laying flat on a very shallow depth, basically like that. That's why I see shore to shore. I can look across this area here, and I can see across there. I can see to Barrow-in-Furness 18, 20, 24 miles away. You know, I've done it from way down here, and you look across this area and it's all very flat. There's no real drop-offs, and that's the point, is that we don't get drop-offs. We don't have any drop-offs in this area. Even if we go out to this location, it's only 10 meters deep here. Only 10 meters deep. Look how far we're going out. Let's just do a measurement there. 10 meters deep, 12 meters deep, and we're 13 miles. Hang on, how many miles are it? Yeah, 12 miles offshore there, and it's only going down to 10 meters deep, 30 feet. So when we're seeing all this stuff, all this localized area, we don't have these massive drop-offs. So when I'm filming these boats and they just disappear and they just blend into an inferior mirage and then disappear due to their angular size, that's essentially what we see. It's because we have a flat area. This area is really flat, and because it doesn't have any underwater topography that's going to, you know, that's anything like what Dazza the Cameraman has here, you know, this massive drop off here, we don't have that. We have this very flat. So because it's very flat, the water lies flat. And here's another point: if we lived on a globe, what you would see is that this liquid, this blue area that's denoting liquid, so that the water, it would have to conform to the bulge of the, well, to the gravitational force of the Earth. So it would bulge. It absolutely would bulge. It wouldn't lie flat. It would be like so, and then it would have to bulge up. It would literally have to bulge up, and it doesn't. It lies flat. And that's because the topography of the land underneath is very level itself. So it's all to do with where you live. You know, if you live in areas where you've got this massive drop off, you've got all kinds of stuff going on. You've got barotropic tides. I'll even go as far to say that in this location here, this, because Tony put in a response about tidal bores, and in this exact location in Morecambe Bay, you get tidal bores, and that's because you've got the incoming tide from left to right here pushing in. So it's pushing into there. This is the bottleneck here. This is the bottleneck, obviously. It's the entrance to the bay, and this is where you're going to get some localized bulging too, just across this particular section. And you know, I've actually got videos up of me filming from this location and seeing obstruction due to the water, and it's in exactly this location at the bottleneck where this Morecambe Bay is. So it's all to do with understanding your topography. You know, if you're going to be filming close to a bay or an entrance like so, what you're going to get is you're going to get a funneling effect. You know, in this case, it's a tidal bore. In the case of Dazza the Cameraman, it's the barotropic tide. But again, it's all to do with understanding the topography of the land. You know, and if you're going to be very, you know, blasé about it and just say that this is Earth curve without actually looking into it. I mean, Conspiracy Cats is one. He says that, you know, because I looked across the location from this location to, so let me just go back so you can see. So when I looked across this here, this area, and I encountered the bottom of the lighthouse being obscured by water, he's instantly referring back to this as being a proof of curvature. No, it's actually a proof that there's something else going on. And when I researched it and found out exactly what it was, and have ample proof if that's the case, that this is called the tidal bore, and the tidal bore artificially raises the height in that location, so it's localized bulging. So there is a small area in my location where you get this localized bulging. There's also another one down here where you get some small localized bulging just down here. So it's worth looking into, guys. And just saying that it's earth curve doesn't mean that it's earth curve. I mean, just saying that it's earth curve, it doesn't mean it's that. Horizon, he's already presupposing that we're living on a curve, and it's wrong, because we're not living on a curve. He's not looking into this barotropic tides, and I wish he would. And if he wants to make a response video, go ahead, knock yourself out, mate. Knock yourself out. Right, again, a very quick one, so I'm going to end this one now. I just wanted it to be pretty concise. Bloody hell, I've waffled on for 25 minutes. Thanks everyone for stopping by. I've given a few shout outs. Jimbo, nice to see you in. And yeah, guys, I'm going to end it now, and I'll see you all in the next one.